Hi everyone, this is a tutorial on how to get NetCDF data in a CF compliant form so that Vapor can read the data. Vapor can read NetCDF data as long as it follows the CF conventions. And so what we're going to do is start with this simple NetCDF file. Over here on the left we can see I've done an NC dump on our simple file, and it describes the dimensions and the variables that exist in the file. We have a time dimension, a z coordinate or a z dimension, a y dimension, and an x dimension. Our grid is 24 by 48 by 48, zyx, and there's one time step. We also have a temperature variable that is a function of time, z, y, and x. But this is about as simple of a NetCDF file as we can get. And what Vapor needs are what are called coordinate variables that describe where these dimensions, or these grid points exist in space. So if we look at the right, we can see a CF-compliant NetCDF file that has these coordinate variables. For example, our x-coordinate variable is named the same as our dimension. So our coordinate variable x is a function of the x dimension, and it has double floating point values that describe where the grid exists along our x dimension. Likewise for y, and likewise for z, and likewise for time. In addition to defining coordinate variables, we're also going to apply attributes to them so that Vapor knows where they exist or which axis they pertain to. So just because our x-axis is named x and it's a function of x doesn't mean that it necessarily is prescriptive for the coordinates of the x-axis. So to fix that, we need to have an axis attribute that is a capital X, and likewise for y, z, and time. And we'll also be adding a units attribute to time, which is going to be seconds since January 1st, 2000. One thing that we don't see in this NC dump is that we'll also be adding units attributes to our other coordinate variables x, y, and z. So that's the basics of what we're going to do. And again, I will be adding links to all relevant documentation and scripts that you'll need to follow along. What I'll be doing in this tutorial is stepping through how to make our data CF compliant with a Jupyter Notebook. I'll be using Python to do it. There's other alternatives. CDO is one that I've used in the past, but for demonstration purposes, Jupyter Notebooks are kind of the de facto thing to do these days. So I'll be stepping through this Jupyter Notebook using Xarray and NumPy. And you can find the documentation if you go to our website and go to Getting Data into Vapor, go to NetCDF, and then there's going to be walkthroughs. Right now we have a walkthrough for regular grids, getting regular grids CF compliant, also stretched grids, getting those CF compliant, and soon we'll have another walkthrough for curvilinear grids. But if you click on the walkthrough for the regular grids, you're going to be able to find basically the exact same steps in this this website, this document, as the steps that I'm going to go through in the Jupyter Notebook. Additionally, you can find the Python script that emulates my Jupyter Notebook through this link right here. You can download this Python script that replicates all these steps, and that's going to go to our GitHub repository. And you can just copy and paste this file and make the changes that you need if that's what you'd like to do. So with that being said, again, I'll add all links to the bottom that are relevant, but let's step through our Jupyter Notebook and go through this process of getting our data to be CF compliant. Again, we're going to be creating coordinate variables, we're going to be giving them axis attributes and unit attributes, and we're also going to be giving a unit attribute to our data variable. And then finally we'll plot the whole thing. So I'm here in my Jupyter Notebook, and the first step is to import Xarray, which is kind of like the data manipulator. That's what we're going to use to open our NetCDF file and modify it so that it has coordinate variables. And then we'll be using NumPy to generate the values for those coordinate variables. So I'll simply run that, and that was easy enough. I'm going to be using the path library just for file manipulation on my local machine, and also this Google Drive downloader. My sample NetCDF file is hosted on Google Drive, and so if you guys want to follow along with the aforementioned Python scripts, Google Drive downloader will be needed on your Python installation. So I'll run that, And the first thing that I'll do is this step basically downloads that Google Drive file and sets my home path. So I'm going to download the Google Drive file to my home path and name it simple1.nc, and then Google Drive Downloader will perform that step, and now I have the simple1.cdf file in my home directory. Next, my dataset variable named ds will be opened using xarray, which I've abbreviated with xr, and the open dataset command on my downloaded simple NC file. And then I'm going to print the info so we can get our first look at what we're dealing with. So xarray.dataset, I have my time dimension, my x dimension, my y dimension, and my z dimension, 48 by 48 by 24. And then my variable, I have a temperature variable, which is a function of those dimensions. So the first thing that we want to do is create our coordinate variables. And the first one I'll make is called time. So I will operate on my dataset object, give it an attribute called time, and then that time coordinate variable will be equal to a function output from NumPy linspace, which is only going to, linspace basically generates a series of numbers that are monotonically increasing and are equally spaced between each other. And so my start point will be 0, stop point will be 0, and it'll just be 1. So I'll run that, and that's my time coordinate variable. To create my spatial coordinate variables, y, x, and z, and again, my spatial coordinate variables need to be have the same name as my dimension. So if I scroll up, again, my dimensions, lowercase x, lowercase y, lowercase z, and lowercase time are my dimensions, and I need to name my coordinate variables the same. So lowercase time is my coordinate variable, likewise for y, x, and z. And again, I'll be using numpy.linspace to generate a monotonically increasing series of values for these coordinate variables, starting at 0, stopping at 100 for x and y, and then the number is going to be 48, the same value as our dimension. And likewise with z, except for z only has 24 data points, and our stopping point will be at 50. So I'll run that. So alternatively, if you have a, not a rectilinear grid, but what we call a stretched grid, where the data points aren't equally spaced, maybe they're closer together at the base, at the low values of your z dimension, and then they get more farther apart as you gain altitude, such as what the WRF model does. You can use other NumPy tools to generate values like NumPy's geometric space, and there's some other alternatives, but you can even enter hand-picked values. But I think most of the time people are already going to have coordinate variables, but if you have to generate your own, NumPy offers a suite of tools that you can use for that. So those are all comments. I'll go ahead and run it, and then I'm going to print my info. So we still have a time, an x, a y, and a z dimension, but our variables, we have now created coordinate variables, a time coordinate variable, y, x, and z, all named the same as their corresponding dimension. The next thing we have to do is assign attributes to our coordinate variables so that Vapor knows where they exist in space and time. So we basically just call dataset.time, our time coordinate variable, and then we can add an attribute with the attributes function. We can name the attribute axis, and we'll assign it capital T for time, likewise for x, y, and z. And so that's going to apply the axis attribute. Now we have to do units. And so our units for time are going to be seconds since January 1st, 2000, and our units for x, y, and z are just going to be meters. For completeness, we're also going to add an attribute for our temperature variable, and we're just going to call it Kelvin. It doesn't matter as much for temperature as it does for our, if your data set has wind vectors. Vapor is going to need to know if it's meters per second, kilometers per second, and that's just to let our flow integrator operate properly. If we don't know how fast your wind speed is moving, compared to the size of your grid, we can't integrate path lines or streamlines. All right, so I'll print out my dataset.info again. Like before, we have time, x, y, and z, dimensionality, but now we have our temperature described in units of Kelvin. Time is on the t-axis. Our units are seconds since January 1st, 2000. Our y-axis corresponds to y. Vapor now knows that y is our y-axis, and likewise for x and z, and that they all have the meters unit. So finally, let's see, we're going to save it to file. So our data set can be saved, Xarray can save a whole multitude of different data file formats. We'll be using 2NetCDF to save this as a CF-compliant NetCDF file. And that'll be in my home directory, and I'm calling it regular-compliant.nc. And for sanity, we're going to plot the result. So this will be looking at, I believe, z equals 0, the very bottom slice of our temperature variable in our data set. So if we want to now compare that, I can open up Vapor, close that, and then go to Import, NetCDF CF for CF compliant data. And in my home directory, I now have modified to 831. That's it, my regular compliant.nc file. I'll click on a new slice renderer. Enable it, and our slice is in the middle of our domain. I'll go to my Geometry tab, where I can move the slice down to the very bottom, click on Home, and do a little comparison. Let's see. Looks a little different, but the color palette is different. So let me fix that. I'm going to go to my Appearance tab, click on my gearbox, and load a built-in color map. This is a diverging map, and I think this is the one. What's it called? Balance. So there's balance. Roughly the same. I think the map plot, lid plot is longer on the x-axis than it is on the y, but this is my sanity check. I can now be assured that my data is now CF compliant. I see it in Vapor. I can see it in Xarray. So that's the basics on how to get generic NetCDF data CF compliant for the regular grid, and it's basically the same step for the stretched grids. If you just look up here, there's a big comment where we're just using geometric space versus linear space. Or if you already have a coordinate variable or coordinate variables for your spatial and temporal dimensions, you don't even have to worry about creating them. All you need to do is add the units and axis attributes to your coordinate variables, and maybe units to your scalar variable. So thanks for watching. I'll again add all links that are pertinent below the video, and please leave comments if you guys have questions or visit us on our forum. And thanks again. Hopefully see you soon. Bye-bye.